defined like this. So the number m sub n is equal to 2 to the n minus 1. So these are numbers that are 1 less than a power of 2. And so this guy, Marin Mersenne, back in the 1600s, was investigating these things, trying to see if, you know, you could find lots of fine numbers from them. And there was some observation, I guess I told you that. We didn't prove it yet. We'll look at it soon. But what turns out to be the case is that if you put a composite number as the subscript here, then this will always be composite. Okay? We're going to prove that right now. Okay, so if you're like out in the hunt for prime numbers and you're hoping these things are prime, what that says is they will never be prime if you have a composite n. Okay, but it doesn't say what will happen if you put a prime down here as the index. So that's what we'll talk about after. But this is the first important thing here about these numbers. So this is state this and prove it. So proposition 2.18. So we'll actually, let me first state the thing we're going to prove, which is this. So if it's the case that a is a divisor of n, so if you have an integer a that divides an integer n, then what's true, in fact, is that the Mersenne number m sub a actually is a divisor of the Mersenne number m sub n. That's what we're actually going to prove first. Okay, and so consequently, what's going to happen then is if n is composite, then m sub n is also composite. Okay, and so, yeah, okay. So because if n is composite, you can find an actual, let's say, a non-trivial divisor of n that's number a here. And then m sub a is going to be a divisor of m sub n, showing that m sub n is composite. And I mean, you might just want to think about the fringe cases for a second. I mean, by the way, if you were considering a to be 1, which would always be true here, m sub 1 is the number 1. So in that case, you don't get something interesting over here, right? It is, you just say 1 divides m sub n. And the other thing just to note, if you were to consider the case where a is n, then this is m sub n, and it's a divisor of m sub n. That's true, but those would be like the case where a is 1 and a is n correspond to the trivial divisors of m sub n over here, where this thing is either 1 or the number itself. Okay, but what's going to happen then if you have any a over here that's neither 1 nor n, you'll actually get an interesting divisor of m sub n, and that's why this follows. So. Anyway, this argument, well, we're going to prove it now. It has like a little just clever algebra trick in it. Okay, so we'll take a quick look at how this gets proved. Okay, so it follows from a algebraic factorization. So I'm going to show you a factorization of a polynomial into a product of two things. So if you have something like this, say a power of x minus 1, you can factor out x minus 1. And what's going to happen here is this is going to be some sort of, well, let me write it first. So what this is the sum of all the powers of x, from k minus 1 down to the power 0. Okay, and anyway, so this is, I mean, probably something you've seen, but if you haven't, you just take a second to make sure you believe it, which is the way you would make sure you believe this is think about expanding the right-hand side, right? So take all these terms right here, multiply them by x, and see what you get, right? Which would be all the sum of powers of x from x to the k all the way down to x to the 1. And then also see what happens when you multiply this minus 1 by all these terms. And then you have negative contributions of powers of x from x to the k minus 1 down to the number 1. And what happens, it's a telescoping sum, basically, where all the terms are going to cancel out except for two of them. The highest power of x and the negative one you have at the end, and that's these two terms. Right? So just make sure you believe it. But anyway, this is, you can view it as a polynomial factorization, which means, it's true, let's say for any x, any number x, and any integer, k, which is, I don't know, should be a positive integer. Let's just, let's say j is 2. No need to talk about it when k is 1, I think. Okay, so anyway, here's the point though. Is a Mersenne number kind of looks like something like this. It's like a power of something minus 1. So we'd like to know if we can take advantage of such a thing. And so what are we going to assume here? Suppose a divides n. So suppose a divides n, and let's say n is a times b for some b, some integer b. Okay, and so what we're going to do to this thing then is write it as follows. Okay, so let's write m sub n. Right, so m sub n is going to look like that, but since n is a times b, we'll write this as 2 to the ab minus 1. Okay, and where we're headed on this thing is we want to apply this kind of a factorization in such a way that this is m sub a. Mersenne number m sub a. Right? We're trying to show m sub a as a divisor of m sub n. So we want to cook it up so that this is m sub a right here. So that would mean x, we would need x to basically be 2 to the a power. And so then this should be 2 to the a raised to some other power. And that power is going to be b. Right? So we're going to write this like 2 to the a to the b minus 1. Like that, and we're going to use this thing over here. So this is just a little side note to help you think about stuff. Just think here, x is 2 to the a, and the k is b in this identity, and we're going to insert those things into that identity and see what happens. So by the identity here, this is 2 to the a minus 1 times what? So it's so the k is b now, and this is 2 to the a. So this is 2 to the a to the b minus 1 power, plus 2 to the a to the b minus 2 power, etc. With lower and lower powers all the way down to 2 to the a plus 1. Okay, so anyway, we're essentially just using that identity, but you can also just write this and make sure you believe this too. You can multiply it out and see the sum telescope the same way, and it should simplify exactly to be 2 to the ab minus 1. And so that's it then. So this is m sub a right here. The other thing is just an integer. I mean, it's some integer, right? That's we don't have a name for it or anything, but just note this is some integer. Okay, and it's built out of all these integers and powers of integers, and so it's definitely an integer. So that's all we really need. So that shows us m sub a is a divisor of m sub n. Okay. So the algebra makes sense. So that's the entire argument. And so we'll take a closer look at this in a second, but then we'll return to just discussing Mersenne primes. But again, the main point is this consequently statement, right? So m sub n will always be composite if you start with a composite index. Okay. Now this is a bit more precise of a statement because it's telling you specific divisors. So something you can do with this if you want to illustrate it or maybe use it is you could consider one of these composite m sub n's and try to factor it by taking advantage of this. So we'll do that in a second, but are we okay with the proof? Any concerns or questions or anything? Okay, so I just want to show you what this result might look like in an example. So anyway, example is something simple to look at. Suppose you look at m sub 10. Right, so this is 2 to the 10 minus 1. So 2 to the 10th power is 1,024. So this is the number 1,023. So anyway, what we know, because we just proved it, is that this is composite. Okay, and if you wanted to factor it, I mean, you could just try, I guess, but we have a little bit of inside information. Let's say we wanted to factor this number. Okay, and so to factor, let's just use what we learned. So, I mean, the thing is that the n here is 10. 10 has some interesting divisors, namely 2 and 5. Right, so we know that 2 divides 10. So what this would imply is that m sub 2 divides m sub 10. Right, and that's what we just proved. And m sub 2, I mean, that's just 2 squared minus 1, which is 3. Okay, so that's telling you something you maybe could have figured out quickly anyway, but this number is divisible by 3. The other thing is a little more interesting that was not so clear. But 5 is a divisor of 10, so that tells you m sub 5 is a divisor of m sub 10. And m sub 5 is an interesting prime number. This is 2 to the 5th minus 1. Right, that's 32 minus 1, so this is 31. So perhaps you wouldn't have guessed that right away, but that number is divisible by 31. Okay, and so now, I mean, you know a good amount of information about this number. You know it's divisible by both 3 and 31. That's going to imply it's divisible by 93. So okay, and so then you could say, well, at this point you've almost won this thing. So if you wanted to figure something else out, you could just do the division and actually figure out what this is. You know, divide it, and the answer is 11, by the way. So if you could actually compute that and say, oh, well, that's 11, so therefore our number 1023 is 3 times 31 times 11. That's actually how it looks as a product. Okay, and so that, I mean, that's just like a small example of trying to take advantage of this fact to accomplish a task like this. Okay, but anyway, we are mostly then, that's an illustration of this proposition, but we're mostly then going to not be too interested in these numbers where the index is composite, because we know they are not primes. So anyway, just building on this. What we've got then is that if, after what we proved, so if m sub p, which is 2 to the p minus 1, is prime, then p must be prime. Okay, but then you ask the question, well, anyway, such an MP is called a Mersenne prime. Right, but then there's a really important point that make sure nobody gets the wrong idea. But there is a question to ask, which is if P is prime, is MP also prime? Okay, and this is the really important part, just to make sure you're aware of this fact. The answer is a big no. In general, no. No, not in general. It is sometimes, and then sometimes it's not. Okay, we were talking a bit about this near the end of the last class, but so when you look at the primes and you look at the m sub p's, you see that some of them give you prime, some of them don't. Okay, the ones and the prime numbers that come out of this construction are called Mersenne primes. So just to give you a small sense of the story here. Okay, so this is true. But not for 11. Okay, so it's prime for the first 4 primes, but not for 11. So I just want to, we mentioned this last time, but just as an aside, M11 is 2047, and that is something 23 times 89, one can show. And so it just doesn't work there. And that's the first counter example that shows you they're not always prime. But it's interesting because it picks back up and check what I've got here. So yeah, the next 3 primes it is prime. So M sub P is prime for, I guess, 13, 17, and 19. But not the next one. Okay, and when you think about these a little bit, by the way, these numbers are getting big, okay, because they are growing exponentially, right, as a function of P. So I'm not going to write that number down, but it's pretty big, okay, already. So, as you keep going and consider these more and more, you have like a pretty big task on hand because these numbers are humongous. They're growing, again, exponentially. Anyway, I just want to say it is, I'll just list a couple more, just FYI. Well, these aren't consecutive, but the next Mersenne primes, I'll just list a few. So M31, and you can see there's a huge gap here. Right? So 31 gives you a prime, 61 does, but nothing in between. So there's, I'll just write a couple. Just pulled off Wikipedia or something. But anyway, as you can see, at this point, thinking what's 2 to the 521 power? It's really, really, really big. Okay. Anyway, there's some more. I'm going to list them all. But anyway, what happens is you run into some questions. There are natural questions that show up once you start digging here, and you can say, well, okay, in the world of Mersenne primes, will there be infinitely many? Like, will there always be more and more Mersenne primes, or will there come a point at which you've hit the last Mersenne prime and none exists past that point? That's an interesting question. Does anybody know the answer to that question? You could become famous if you learn the answer to this question, or if you figure out the answer to this question. Nobody knows the answer to that question. So anyway, I'll just leave this point here. It is unknown. If there are infinitely many Mersenne primes. Okay, just nobody's figured it out. We don't know. We know there are infinitely many primes, but this is a different question. Are there infinitely many primes that have this specific form of 2 to the p minus 1? Okay, we don't know. Interestingly, though, we mentioned the largest known prime number currently. Right, so currently the largest known prime as of 2024, right? That was when it was found, is a Mersenne prime. And I mentioned it here, I think I wrote what it was on the board previously, but it's this one. Okay, so that index of whatever that is, that's turned out to be a prime with the property that this thing is a Mersenne prime. And so anyway, these things, because they have a certain kind of structure, they all look like this. There's certain tools kind of adapted to testing whether or not they're prime, like some advanced techniques. But if this number has something like 41 million digits or something, and if you have a random 41 million digit number in front of you, you're not going to have a good technique to tell if it's prime or composite. But on the other hand, there's techniques adapted to these numbers that can, it uses a lot of computational effort, but it can be sort of determined. Okay, so anyway, this is where people look, usually, when they're looking for larger and larger primes, if that's their interest, is they're checking out the Mersenne numbers, like putting different larger and larger primes down here, and they're trying to test these computationally. The interesting thing as it relates to this question, actually, I was telling you all these ones, we've got all these Mersenne primes, I was listing some over there, and we've got up to here. There's actually only 52 known ones. There are only 52 known Mersenne primes. So there's probably fewer than you would have guessed, maybe, based on how this discussion was going, but there's 52 known ones up to about here, I guess. I would assume they've tested everything in between the number 2 and this base here, but I'm not totally sure. Okay, so anyway, that's that. So anyway, it's an interesting conjecture, though. People don't know. I think people think the answer is yes, like as far as nobody proved it, but that's the general, I think people's biggest thing. The experts kind of think it's probably true, but don't know how to prove that. Okay. You have a question?
Yeah, out of curiosity, is it known whether or not there's an infinite number of Mersenne numbers with prime exponents that are composite?
That's a good question. I mean, I'm not sure about that. There's a good chance the answer to that's also known, but I mean, it's not known.
Not known.
But I mean, I'm not really sure. I could ask somebody about that, but that feels like one of those things that everyone definitely believes is true and no one's proved. But I'm not sure about that actually. And don't look into that one. Good question. No, that's a good one. Okay. Do you guys have any other questions? Yeah.
I mean, how would a proof like that go? Like, how would you?
Well, nobody knows. That's the problem.
Yeah.
We proved there are infinitely many primes.
Yeah.
You could also, if you knew less than you knew right now, you could say, well, how could such a proof go? How could you actually prove there's infinitely many primes? And I mean, it was kind of a clever argument. It goes back to Euclid we gave, but I mean, yeah, it's perhaps unclear. But we gave a non-constructive proof by contradiction that there are infinitely many primes, which is we assumed there were finitely many and we found a contradiction. But the proof is non-constructive in the sense that we never explained how to build one. Right? That's what that means. So I mean, in theory, maybe you could do that. There's something else that there's a chance we'll talk about way, way down the line in this course where there are these things called perfect numbers, which have a curious property that basically the sum of their proper divisors equals themselves. And there's an interesting link that there's a one-to-one correspondence between even perfect numbers and these numbers, these Mersenne primes. It's a bit of a surprising link. But there are things like this in number theory, so if someone could prove there are infinitely many even perfect numbers, they would tackle this problem, but still no one knows how to do that. So anyway. So it's unclear how to proceed, but it's it's an interesting thing. A lot of times in number theory, you just run into these kinds of questions, and no one really knows what to do about it. There's a lot. I guess number theory is notable for having a lot of unknown problems, unsolved problems that are kind of easy to state and understand. Like everyone understands the question, I hope, but we don't know the answer. Okay. So anyway, it's just supposed to be sort of a fun thing. I told you that people use large primes in cryptography. Maybe you know a little bit about that, maybe you don't, but we'll learn some this semester. But nobody's using these primes in cryptography. They're too big. Those are more like primes that have several hundred digits, not primes of 41 million digits. So this is just people fighting for world records. Okay, so anyway, that's a little bit of a fun diversion, I guess. We're going to look at something similar in a second called Fermat primes. So it's sort of a different attempt at building primes. So I mean, this is this was Mersenne attempt at generating primes, was looking at these numbers. It's unclear if Mersenne succeeded, right? We don't know if Mersenne succeeded. But something different, we're going to look at Fermat numbers. So instead of looking at numbers like we just did, so numbers of the form, well, we just did, 2 to the n minus 1. So Fermat, whose name we'll hear a couple times, so Fermat looked at numbers that have a plus here instead of a minus. Okay. So we can consider that. It's really a totally different story the way it pans out. I mean, so you can consider different m's there, and maybe it's interesting just to look at the first couple examples. I mean, I guess you can consider m equals 0 if you want, because that works, right? That gives you get 2. You look at m equals 1, you get 3. You look at m equals 2. I guess you get 5, right? It's looking good. Okay, if you look at m equals 3, this is 8 plus 1, which is 9, right? That's no good. 9 is 3 times 3. So that's, the answer, whatever happens here is definitely different than what happens with Mersenne numbers, because we have this number 3 where it just goes wrong. Okay, so it's actually a different story here. And what happens, with these numbers is that you're going to get something composite if you don't have a power of 2, actually. So this is composite. Unless m is a power of 2. Maybe we'll not worry so much about that 0 example, but so the fact that the m here was not a pure power of 2, it was in fact 3. So this would mean we'd be considering things that look like m equals 2 to the n. So essentially 2 to the 2 to the n plus 1, things like that. So we'll prove this first, though. So this is going to have a proof which is similar to what we just did with Mersenne numbers, where we explained why the Mersenne numbers with a composite n have a divisor. Do you want to?
What about m equals 0?
Yeah, I wanted this crossed off the list, I think, because it's a bit of an oddball case. I mean, you could argue it works, but let's just forget it, because that's for positive m, this is definitely true. So if m is positive, this will be composite unless it's a power of 2. Okay, so we're going to prove this. This is let's state it properly. So proposition, say 2.19. So let's say that we'll assume m is positive. Let's say it's greater than 1. So if this is not a power of 2, then 2 to the m plus 1 is composite. That's the statement. Okay, so the way we're going to use this not a power of 2 thing is that numbers that are not a power of 2 have odd divisors. Will have an odd divisor. It must be divisible by some odd number. Okay, I mean, that's certainly true. Okay, and trying to figure out if we're actually using properties of prime factorizations. But that's going to be the key thing. So we're going to show that if m has an odd divisor, then 2 to the m plus 1 is composite. going to go is similar to our Mersenne proof. We had a little algebraic factorization. And so the thing here is, recall, it's just another polynomial factorization. But you need an odd number in the mix. So we want to basically have a factorization of something like this. So x to the k plus 1, right? And so there's a bit of an even-odd problem, and it's probably kind of evident when you think about some small examples. Like when k is 3, this is a sum of two q's, and you've probably seen a way to factor it in your life at some point. Like how do you factor x cubed plus 1? You could factor out an x plus 1 from it. You've probably seen something like that before. But if k is 2 and you say, I want to factor x squared plus 1, that's kind of a problem unless you're willing to use complex numbers, which we aren't really willing to go there right now. We're trying to work with integers. Right? So there is actually an even-odd problem here, where sometimes you can factor this nicely algebraically, and sometimes you can't, and it has to do with k being odd. If k is odd, you can factor out an x plus 1. Okay, and it's just another sort of telescoping thing. But what happens here is there's alternating signs. Okay, but what needs to happen at the end is you need to get a plus 1. And that, whether or not this alternating sign business would end with a plus or a minus has to do with whether or not k was even or odd. And when k is odd, it's going to work out. Whereas if k was even, that wouldn't work out. So anyway, that's, you can ponder this as deeply as you like, but this is true whenever k is odd, and that's what you want to take advantage of. So what we'll say then is, if m is not a power of 2, then it has an odd factor. So this would be a number, let's say, let's call it k. So this is supposed to be not 1. Let's also make that 1. Okay, so what we can do then is let's write what we're calling it m as let's say, I don't know, k times a. Okay, where k is odd, as written right here. Okay, so what happens here? Okay, so the point is similar to the other proof, though, is we're going to consider, just write it out. So we have, right, so we could write 2 to the m plus 1 as 2 to the k a plus 1. Okay, and then the point is basically to think of the x here as 2 to the a. So this is 2 to the a to the k plus 1, like this. Okay, and then now we can apply this factorization using the fact that k is odd. So this is going to look like 2 to the a plus 1 times 2 to the a to the k minus 1 plus 2 to the, minus 2 to the a to the k minus 2, etc. Okay, but I mean the point is we're just rescued by this factorization. And point then is that this is a non-trivial divisor. So and I mean that's the proof, and so that shows it's composite. I guess notably it's yeah, k is supposed to be greater than 1. it could be the case that m was, if you want to just think about this for a second, like when m was the number 3, what happened? But we considered that a little bit ago. 2 to the 3 plus 1 is 9. We knew it was composite. If m is the number 3, then in this proof, k is the number 3, and actually a is the number 1, which is okay to have in the proof. And this is still a non-trivial divisor. That's 3. It would be like 2 to the 1 plus 1. So that's, yeah. Okay. Anyway, that's the point. So then where Fermat's discussion leads us is that we have a lot of numbers we shouldn't consider if we are hunting for primes, right? So we should only consider things that look like this if we're looking for primes. Okay, so okay, so then as we just said, for 2 to the m plus 1 to be prime, m must be a power of 2. Okay, so then you can define Fermat numbers. So we'll call it f sub n. But it's going to be 2 to the 2 to the n plus 1. And to be clear about this, so we don't get confused by algebra, this is 2 to the this plus 1, not 4 to the n plus 1. So it's not like 2 squared to the n, it's 2 to the 2 to the n power. Yeah.
So all of our, like, I guess the entire proof hinges on the fact that we have an odd number. What if we have a number like 6, right? Like 6 isn't a power of 2, but it's also not odd.
It has an odd divisor.
It has
It's
an
not
odd
odd,
divisor.
right?
Right,
That's the thing.
yeah.
So, yeah, I think there was something we sort of did here that was a little bit of a, I feel like we're appealing to prime factorizations or something, which we improved a little bit. But the character, and maybe I'm wrong on that, I didn't think on it at all, but we're basically saying that numbers that are not powers of 2 are the same thing as numbers with odd divisors, at least for numbers bigger than 1. So that's really the key thing. So I know that we could have restated this and maybe just said if the number m has an odd divisor, then this number is composite. But that's, I mean, what we said is true, but I'm just thinking maybe that needs to be justified by knowing some facts about prime factorization. But anyway, then, oh yeah.
What happens if m is prime? Because then the only odd divisor, discounting 2, would be like the number itself, right?
Yeah, but it's,
Oh,
it works. The argument goes through. So this is what I was, I mean, it's the same, what happens is the same as what I was trying to talk through with the number 3. Like if m is
yeah,
3.
okay.
So what happens is, like a could be 1 actually, that's okay.
Mhm.
So if this is a prime, it could be p times 1. But what happens in this proof is you still get a non-trivial divisor, because if this is 1, then this is a 3.
Yeah.
So what should be true then, you can check it if you want, is that 2 to the p plus 1 should be divisible by 3, like all the time, I guess. At least as long as p is not 2. So that's, yeah. So the argument still goes through. Okay. So anyway, these are the only numbers that have a chance. That's the end. I mean, that's the bottom line of the story, was that if you're looking for primes, as Fermat was, you have to look at these numbers if you're looking for primes of this form. And so what happens then, if you want to list some, here's how Fermat's search goes. So, you know, there's f sub 0, which is 2 to the, be a little careful, 2 to the 2 to the 0 plus 1. So that's 2 to the 1 plus 1, which is 3. Okay, and so that's a prime. Okay, and then there's f sub 1, which is 2 to the first power plus 1. So that's 2 squared plus 1, which is 5. Right? right, also a prime. Okay, and so f sub 2 is 2 to the, 2 squared plus 1. That's 2 to the 4th power plus 1. So this is the number 17, right, also prime. Right, so what happens is as you keep going, this exponent is going to keep doubling. Right, so f sub 3, right, this is 2 to the 2 cubed plus 1, so 2 to the 8th plus 1. This is the number 257. You guys know if that's prime? I mean, maybe not, but spend some time on it. You can probably figure out it is, in fact, prime. So anyway, this is a bit instructive to see where the search is going. If you look at the next one, this is 2 to the 16th power plus 1, which is actually the number 65,537. So I mean, these numbers are growing like very fast. It's like an exponential of an exponential. So they're growing quite fast. And that is certainly unclear what's going on, but it actually is prime. So this is prime. So these are all prime so far. Okay, so our friend Fermat, with the limited evidence in front of him, I guess conjectured these are all prime. So Fermat conjectured Fn is prime for all n. Did I give you Fermat's dates? I don't remember. Oh, yeah, it's like 1600s, like early, long time ago. So early 1600s. Now, if you go to the next one, like here's the issue, right? So if it's the 1600s, and you look at this number, right, that's F5, that's the next one. And you say, well, is that prime or composite? It's not so obvious, okay? And so what are you going to do, especially if it's the 1600s, right? Is you're going to, unless you've got some good ideas, you probably would just try to do some sort of brute force attack and just find a divisor. See if you can find a divisor, or maybe you just don't. So what happened, though, actually, interestingly, is according to, Euler. Euler is this happened in about 1732, so maybe 100 years after Fermat or something. But Euler figured out, and Euler did not do something stupid. Euler was not just brute forcing his way through numbers. I think he had a good idea. But what he found was that 641 had to be a divisor. And so here's what happened to Fermat's story right here. Was that Euler found out that F5 factors is 641 times this thing, which I believe is also a prime as well. Right? Those are the two prime factors of this number. So anyway, Fermat's conjecture didn't work out so well. Anyway, the thing is that, this is all that we found so far, I guess. So these numbers over here, these are called Fermat primes, kind of like Mersenne primes. So these numbers that come out of this construction, which turn out to be primes, are called Fermat primes. So F5 is not a prime, so it's not a Fermat prime. And so it turns out there are no other known Fermat primes. Okay, so this is a bit of a challenge to work with some of these, because these are even growing faster than the Mersenne numbers grow. So these numbers get out of hand quite quickly. Anyway, a lot of these are known to be composite, but there's no other known Fermat primes. This is also another one of these things. No one's proved whether or not there are infinitely many Fermat primes. So what people think, this one goes a little bit of a different way where people don't really think there are anymore, but they don't know for sure. Some people believe this is it too, like there's no more after this point, but that's also not really known. But there's, so it's just another confusing story here where, again, we don't know if there's infinitely many or finitely many or what. Probably to this question, I don't know. Not sure if there's infinitely many known it's known that there are infinitely many composite ones, okay, but anyway. So, anyway, that's sort of the story. I mean, we'll touch upon these things a bit later in the course too. We'll just kind of return to them to explore some ideas we see later in the context of these things. And so, somewhere far down the line, we'll get some insight into what Euler did right here. As I told him, Euler had a good idea. So Euler found a good way to kind of narrow down what the possible divisors of such a number would be. So that's something we'll encounter a bit later. Okay, but so in some ways this is kind of like supposed to be mildly amusing, somewhat fun sort of sections playing around in recreational mathematics. But some of these things we'll encounter again, and gives us a chance to explore some ideas. So, I mean, that's pretty much it as far as these go. I just said a couple of things. I'll just scribble something. So, not known if there are any more, or infinitely many, or anything like that. Okay, so it's probably a good time to stop. So next thing we're gonna do is something a bit different. We're gonna start talking about Diophantine equations, just something totally different. And I'll just leave you with one note, just one last thing to consider. Just something you might want, if you want to play around with some idea. Maybe think about what happens if you don't use 2 here. Either in Fermat's type of example or Mersenn's type of example. Like what if you want 3 to the p minus 1 or something, or you'll realize there's a problem with that. You think on it a little bit. Or what if you want to do like what Fermat did with 3 to a power